The cosmos resists any ultimate final explanation. This is not due to any lack of intellectual prowess on our part, nor is it because the mathematics involved is insurmountably difficult. It is because the essential character of existence itself pushes back against being confined within a singular, exhaustive, and definitive account. On each occasion, we believe we are nearing a comprehensive theory of everything. The universe unveils an additional stratum, a further intricacy, yet another demonstration of why absolute completeness is unattainable. I am Leonard Susskind, and following a lifetime devoted to the pursuit of foundational theories, working within string theory, quantum field theory, and holography, I have arrived at a clear and perhaps humbling realization. The universe may, at its core, decline to be encapsulated by any final theory. Allow me to elaborate on why this could be the case and what implications this holds for the field of physics. When I state that the universe refuses a final theory, I must define my terms with precision. A final theory, often envisioned as a theory of everything, would constitute a total account of reality from which every physical phenomenon logically proceeds. A single set of equations, one overarching framework capable of elucidating everything, from the behavior of quarks to the formation of galaxies to the very nature of conscious awareness. This has represented the central aspiration of physics for hundreds of years. Isaac Newton believed he had achieved it with his laws of motion and gravitation. Albert Einstein pursued it relentlessly with his quest for a unified field theory. Proponents of string theory feel they are approaching it with M-theory. Yet I have grown to suspect this dream is inherently unachievable, not due to any deficit in human ingenuity, but because the architecture of the cosmos is fundamentally constructed to repel any final description. The universe denies us a final theory because reality possesses a depth that transcends the capture of any theoretical construct. Let me present the first reason: Gödel's incompleteness theorems. In 1931, Kurt Gödel demonstrated that within any formal system of sufficient complexity, there exist statements that are true, yet cannot be proven using the rules and axioms of that system itself. The system is inherently and necessarily incomplete. Now, can we consider the universe such a formal system? If the laws of physics can be expressed mathematically, then the answer is likely affirmative. Gödel's theorem intimates that there will be truths about the cosmos which cannot be logically derived from any finite set of foundational axioms. A final theory would precisely be such a set of axioms from which all physical truths follow. However, Gödel informs us that for any proposed set, there will be physical truths that lie outside its scope, requiring additional postulates. One can always extend the theory, appending more axioms, but this newly extended framework will then generate its own collection of unprovable truths. It becomes a perpetual ascent of axioms, one after another, never arriving at a state of absolute completeness. The universe rejects a final theory because Gödel proved that systems of sufficient complexity are intrinsically incomplete. Next, allow me to discuss the halting problem and the concept of uncomputability. Alan Turing established that no universal algorithm can exist to determine whether an arbitrary computer program will eventually halt or run forever. If the universe is computable, if it operates akin to a vast computer executing according to physical laws, then the implications of the halting problem apply. There exist questions regarding the universe's evolution that no algorithm, and thus no theory, can definitively answer. A final theory ought to predict the behavior of the cosmos from any given starting conditions. Yet, if the universe encompasses processes that are fundamentally uncomputable, then no theory can offer a complete prediction of its evolution. Quantum randomness may be computable in a statistical sense, but certain cosmological questions, pertaining to infinite universes or eternal inflation, for instance, might involve genuine, irreducible uncomputability. The universe refuses a final theory because some of its aspects may be essentially uncomputable. Let me now turn to observer dependence and complementarity. Within quantum mechanics, the outcome of an observation is contingent upon what one chooses to measure. Different measurement procedures yield information that is fundamentally incompatible. One cannot know both the precise position and the precise momentum of a particle simultaneously. This principle extends to black holes through the concept of black hole complementarity, where descriptions of the interior and the exterior are complementary and cannot be employed concurrently. It further extends to cosmology. Different observers, situated behind different cosmic horizons, have access to different observable universes and different sets of information. A final theory should, in principle, describe reality in an objective manner, independent of any observer. However, quantum mechanics and general relativity collectively inform us that reality is observer-dependent. There is no privileged view from nowhere. Any theoretical description is necessarily framed from a particular perspective, utilizing a specific measurement framework. Alter the perspective, and you necessitate a different description. There exists no single, final description capable of capturing all possible perspectives at once. The universe refuses a final theory because reality is fundamentally observer-dependent and perspectival. Now let me consider the landscape problem within string theory. String theory was initially heralded as the potential final theory, uniquely determining all physics from first principles. However, it has since been revealed that string theory admits approximately 10,500 possible vacuum states, each corresponding to a different set of physics, different particles, and different forces. Which one describes our universe? The theory does not offer a unique prediction. It does not determine which specific vacuum we inhabit. This landscape might be an intrinsic feature, not a flaw. In scenarios like eternal inflation, all possible vacua may be realized somewhere within an infinite multiverse. Our universe is merely one bubble among this vast ensemble. Consequently, inquiring why we inhabit this particular vacuum transforms from a pure physics question into one of anthropic selection. If this viewpoint is correct, then the final theory is actually the theory of the entire landscape, but it does not uniquely predict our specific universe. It predicts a colossal ensemble of possibilities, and we find ourselves within one element of that ensemble that happens to permit observers. The universe refuses a uniquely predictive final theory because the fundamental framework may predict an entire spectrum of possibilities, not a single, unique cosmos. Let me elaborate on effective field theory and the endless tower of approximations. At every accessible energy scale, we possess an effective theory that functions with remarkable precision. Newtonian mechanics operates at low speeds and energies, special relativity at higher velocities, general relativity in strong gravitational fields, and quantum field theory at microscopic scales. Each of these is an approximation to a deeper, more fundamental layer. Newtonian mechanics emerges from Einsteinian relativity. Classical field theory emerges from quantum field theory. It is plausible that quantum field theory itself emerges from string theory, and perhaps string theory emerges from something even more basic. Does this process have a terminus, or is it a perpetual descent of effective theories, each valid within its own regime, yet each merely an approximation to deeper levels that are themselves approximations? We have never discovered a definitive bottom layer. Each time we probe more deeply, we uncover further structure. What reason do we have to believe this sequence concludes? The universe might reject a final theory because it could be effective theories indefinitely, with no ultimate foundation. Now let me address the issue of self-reference and the observer problem. A final theory should describe everything, including observers, including scientists performing physics experiments, including the very process of constructing theoretical models. This inevitably introduces self-reference. The theory must account for systems sophisticated enough to comprehend the theory itself. It must explain its own comprehensibility. Gödel's theorems are pertinent here as well. A system cannot furnish a complete and consistent description of itself. If the universe contains observers capable of formulating theories about the universe, then a complete self-description becomes an impossibility. The universe refuses a final theory because any such theory would need to fully describe systems that are capable of understanding it, a task that is self-referentially impossible. Let me discuss the quantum measurement problem and the elusive boundary between quantum and classical descriptions. A final theory ought to explain the origin of classical reality, clarifying how measurement occurs and why we observe definite outcomes. Yet, Every major interpretation of quantum mechanics handles this dilemma differently, and we possess no experimental means to determine which is correct. The Copenhagen interpretation posits measurement as a fundamental process. The many-worlds interpretation denies this necessity. Objective collapse theories introduce new physical principles. The measurement problem has remained unresolved for a century. This is not because we lack sufficient intelligence, but because the problem inherently involves the boundary between the theory and its application, between the quantum system and the classical observer. A final theory must explain this boundary. However, this boundary includes us. It encompasses the very process of observation that renders the theory meaningful. How can a theory provide a complete explanation for its own applicability? The universe refuses a final theory because the quantum classical boundary, which any final theory must elucidate, intrinsically involves the theorists themselves. Now let me address infinity and the procedure of renormalization. In quantum field theory, calculations of loop diagrams often yield infinities. We manage these through renormalization, introducing cutoffs and absorbing the infinities into redefined parameters. This functions brilliantly as a technique within effective field theory, but it simultaneously signals that the theory is incomplete. These infinities indicate there is new physics at higher energy scales that we are not accounting for. String theory claims to resolve these infinities by replacing point-like particles with extended strings. Yet, string theory contends with its own infinities and ambiguities, its own requirement for a non-perturbative completion. Perhaps these infinities are conveying something fundamental, that any mathematical description of reality will inevitably encounter singularities, divergences, and limits where the description fails. The universe refuses a final theory because infinities persistently emerge, signaling inherent incompleteness no matter how profoundly we probe. Let me explore the cosmological constant problem and the issue of fine-tuning. The observed density of dark energy is approximately 10^120 in Planck units. When we calculate what quantum field theory predicts it should be, we obtain a value roughly 120 orders of magnitude larger. This stands as the most inaccurate prediction in the history of physics. Why is the cosmological constant so extraordinarily minute, yet not precisely zero? No fundamental theory provides an explanation. The string theory landscape, combined with anthropic reasoning, offers one answer. The constant varies across a multiverse, and we observe a small value because larger values would not permit the formation of galaxies and life. However, this implies the theory does not uniquely predict the constant's value. It is selected by environmental conditions, not determined by fundamental law. Fine-tuning problems of this nature suggest that the unique fundamental predictions we seek may not exist. The universe might simply decline to provide them. The universe refuses a final theory because fine-tuning problems appear to demand environmental, rather than purely fundamental, solutions. Now let me address consciousness and the so-called hard problem. A final theory should account for all phenomena, including consciousness and subjective experience, qualia. Yet we have no coherent idea how to derive conscious experience from physical law. We can describe brain states and neural correlates of consciousness, but not why there is something it is like to be conscious. Perhaps consciousness is itself a fundamental aspect of reality, not derivable from physics. In that case, a final theory would need to incorporate axioms about consciousness, rendering it less fundamentally reductionist than we might hope. Alternatively, consciousness may be deeply intertwined with quantum measurement, with observation, and with the observer problem. If so, explaining consciousness necessitates solving the measurement problem, which, as we have seen, is entangled with self-reference. A final theory cannot be complete without accounting for consciousness. Yet accounting for consciousness seems impossible within the current boundaries of physics. The universe refuses a final theory because consciousness appears to resist reduction to purely physical law. Let me discuss time and the problem of the present moment. Physics, in its fundamental formulations, lacks a notion of now. It possesses no intrinsic arrow of time, no flow from past to future. The equations are symmetric with respect to time reversal. Nevertheless, we experience time as flowing. We perceive a present moment and a distinction between past and future. From where does this arise? The increase of entropy in thermodynamics offers one answer, but entropy is an emergent statistical concept, not a fundamental one. A truly fundamental theory should not need to rely on emergent concepts for such a basic aspect of experience. The problem of time within quantum gravity is even more severe. The Wheeler-DeWitt equation contains no time variable. Time is argued to be emergent, arising from correlations within a timeless quantum state. But if time is emergent, how can the fundamental theory itself be written? Theories are conventionally formulated as equations describing evolution in time. If there is no fundamental time, what does the theory actually describe? The universe refuses a final theory because time itself is profoundly problematic, emergent in some formulations, absent in others, always resisting a fundamental description. Now, let me address the multiverse and the associated measure problem. In eternal inflation models, different regions of space-time inflate at differing rates, generating an infinite ensemble of bubble universes. Our observable cosmos is one such bubble. To extract predictions from such a model, we require a measure, a method to determine what is typical or probable within this infinite ensemble. However, there exists no unique, naturally defined measure. Different proposed measures yield different predictions. This is the unsolved measure problem. In the absence of a measure, eternal inflation makes no definite predictions. With different measures, it makes conflicting predictions. A final theory should inform us what we should expect to observe. But if the theory predicts an infinite multiverse and we cannot uniquely define what is typical within it, then the theory fails to yield unique predictions. The universe refuses a final theory because multiverse cosmology leads to measure ambiguities that prevent unambiguous forecasting. Let me consider emergent space-time and the consequent problem of formulation. If space-time itself is emergent from more fundamental quantum information, as suggested by holographic principles, then the fundamental theory cannot be formulated using the language of space-time. Yet virtually all of physics is traditionally formulated within a space-time framework. Fields exist on space-time, particles move through space-time, evolution occurs in space and time. If space-time is not fundamental, we require a radically different mode of formulation. What would a theory that lacks space-time even resemble? How does one write equations when one cannot employ spatial and temporal coordinates? Some approaches exist: matrix models, tensor networks, other abstract mathematical structures, but they remain far from a complete framework. We lack a clear paradigm for conducting physics without space-time. If the fundamental theory must be expressed without the very concepts it is supposed to derive, how can we even begin to write it down? The universe refuses a final theory because the theory cannot be coherently formulated using the emergent concepts it is intended to explain. Now, let me address experimental limitations and the Planck scale. To directly test theories of quantum gravity and probe the deepest levels of reality, we would need to reach energies around the Planck scale, approximately 1019 GeV. This is fantastically beyond our technological capabilities. The Large Hadron Collider operates at about 10⁻⁴ GeV. A Planck scale accelerator would need to be the size of a galaxy and would consume more energy than is available in the observable universe. We cannot experimentally test the fundamental theory in its native regime. We can search for indirect signatures and low-energy consequences, but we cannot directly probe the domain where the theory primarily operates. Without experimental guidance, how can we ever know if we have found the correct theory? We must rely on mathematical consistency, theoretical elegance, and indirect tests. Yet, multiple distinct theories might satisfy these criteria. The universe might refuse a final theory by rendering it impossible to definitively verify, leaving us with a plurality of internally consistent possibilities. Let me discuss the problem of initial conditions. Even if we possessed a final theory perfectly describing the laws of physics, it would not uniquely determine our universe without also specifying initial conditions. Why this particular universe? Why these specific initial conditions at the Big Bang? A final theory of laws alone does not answer this. Some propose that initial conditions are determined by quantum cosmology, by a wave function of the universe. But this merely pushes the question back. What determines that specific wave function? Perhaps there are no initial conditions. The universe is eternal, without a beginning. Or perhaps it is a quantum entity with no classical initial state. These proposals still fail to answer why this particular quantum state exists rather than another. The universe refuses a final theory because even flawless knowledge of dynamical laws does not specify which universe we inhabit without a separate, unexplained specification of initial conditions. Now, let me address the criteria of beauty and elegance. In the absence of direct experimental tests, physicists often appeal to aesthetic principles, beauty, elegance, mathematical naturalness, to evaluate candidate theories. But is the universe obligated to conform to our human standards of beauty? The history of science shows that nature does not always align with our aesthetic preferences. Quantum mechanics is not elegant in a classical sense. It is profoundly weird and counterintuitive. The standard model of particle physics is often deemed ugly, with its many free parameters and seemingly arbitrary features. Yet it works with exquisite accuracy. Perhaps the universe is indifferent to our notions of beauty. Perhaps the final theory, if it exists, is messy, complicated, and inelegant. But if that is the case, how would we recognize it? Without decisive experiments to perform, and without beauty as a reliable guide, how do we distinguish the true fundamental theory from an infinite array of plausible imposters? The universe refuses a final theory by declining to conform to our aesthetic judgments about what such a theory should resemble. Let me examine the anthropic principle and how it undermines the quest for finality. The anthropic principle states that we observe a universe compatible with our existence because if it were not, we would not be here to observe it. This explains some apparent fine-tunings. Why is the cosmological constant small? Because universes with large values do not allow galaxies or life to form. Why are the constants of nature life-permitting? Selection bias. However, anthropic reasoning effectively replaces fundamental explanation with teleology. Instead of deriving a parameter like the cosmological constant from first principles, we say it must be small because we exist. If anthropic reasoning becomes necessary to explain features of our universe, then a purely fundamental, self-contained final theory does not exist. We would have fundamental laws plus environmental selection within a multiverse. The universe refuses a final theory because some of its most salient features require anthropic, rather than purely fundamental, explanations. Now, let me address the nature of scientific revolutions and paradigm shifts. Thomas Kuhn demonstrated that science does not progress in a linear, cumulative fashion toward final truth. It undergoes periodic paradigm shifts, revolutionary changes in the fundamental framework of understanding. The transition from Newtonian mechanics to Einsteinian relativity was a paradigm shift. The advent of quantum mechanics was a paradigm shift. Each time, the old theory is not merely refined, but is replaced by something conceptually distinct. Why should this process ever terminate? Why should there not be paradigm shifts beyond string theory, beyond holography, beyond whatever we currently consider fundamental? Every generation of physicists has believed they were nearing final truth. Newton thought so. Einstein thought so. We, in our time, may think so. All were mistaken about finality. Why should we be the exception? The universe refuses a final theory because the history of scientific revolutions is open-ended, with no necessary or obvious stopping point. Let me consider mathematical consistency and the problem of uniqueness. A final theory should be mathematically consistent, free of internal contradictions and anomalies. String theory often claims a kind of uniqueness on this basis, argued to be the only consistent quantum theory of gravity in certain dimensions. But the claim of only consistent theory is immensely strong. How can we be certain we have explored all mathematical possibilities? The landscape of mathematics is vast. Perhaps there exist other consistent theories we have not yet conceived. Furthermore, consistency alone does not guarantee correctness. Multiple theories, mutually incompatible with one another but each internally consistent, might exist. Consistency is a necessary condition, but it is not sufficient. The universe might refuse a final theory by admitting multiple, mathematically consistent, yet mutually exclusive, descriptions of reality. Now let me address the role of human language and conceptual frameworks. Our theories are formulated using language and concepts. But language and concepts are human constructs, evolved for navigating the macroscopic world at human scales. Can we truly describe a fundamental reality that may operate on scales and principles utterly alien to our everyday experience, using tools shaped by survival on the African savanna? Quantum mechanics already strains our language and intuition. Holographic duality strains them further. It is possible that fundamental reality is ineffable, beyond the reach of language, describable only in abstract mathematics, but not conceptually comprehensible. We might be able to manipulate the equations without ever genuinely grasping what they signify. If comprehension requires human-adapted concepts, and reality transcends those concepts, then a final theory might exist mathematically while remaining forever incomprehensible to us, a profound form of epistemic incompleteness. The universe refuses a final theory we can understand, because reality may transcend the very conceptual frameworks that make understanding possible. Let me express why I find this perspective simultaneously disheartening and profoundly liberating. It is frustrating because I have dedicated my professional life to the search for fundamental truth, and this analysis suggests we may never achieve final, complete understanding. Yet it is liberating because it implies that science is an endless endeavor. There will always be another layer to uncover, another mystery to solve, another horizon to pursue. The universe remains inexhaustibly rich. And perhaps this is fitting. Why should reality, in all its complexity, be fully capturable by finite minds within finite time? Perhaps the universe's essential richness, its depth, its inexhaustibility, is a core feature of its nature. The universe's refusal of a final theory means physics remains perpetually fascinating, never finished, always presenting new puzzles to engage our curiosity. Now, let me address what we can achieve, even in the absence of a final theory. We can develop and master effective theories, learning how reality operates across different scales, and making extraordinarily accurate predictions within various regimes. We can uncover deep principles, symmetries, conservation laws, dualities, that connect different descriptions and reveal an underlying coherence. We can explore the landscape of physical possibilities, understanding why our universe has the features it does, even if we cannot derive them uniquely from first principles. Science does not require a final theory to be spectacularly successful and profoundly meaningful. Comprehending layers of description, their connections, and their effective domains constitutes profound knowledge, even without finality. The universe refusing a final theory does not render physics futile. It renders it perpetual. The universe refuses a final theory, and perhaps within that very refusal, we encounter a deeper insight than any equation could furnish. That reality is vaster than any description, richer than any framework, and more wondrously mysterious than any formulation we can devise. This is not a counsel of despair. It is an invitation to humility, to sustained wonder, and to the recognition that the cosmos is more subtle and boundless than we ever imagined. We will persist in doing physics. We will continue to make progress and to understand more. But we should relinquish the hubristic dream of final, complete knowledge and instead embrace the endless, exhilarating adventure of perpetual discovery. The universe refuses a final theory, and that may be the most significant and humbling lesson we have yet learned about the nature of reality itself.